the model you have developed follows the pattern of this data. Let's say this is my. So as much as possible, I want the model that I developed to follow the pattern of this data. Is that clear? That's my goal. The model I have developed, I want it to follow the pattern of the particular data that I have. Now, if it follows the pattern of the data, it means that what? I can use it to what? To predict. It's already following the pattern in which the data follows. And so with that, I have my model fitted to the data. I can now use it to what? To predict into the future. Now, the importance of parameter estimation, it is crucial for fitting models to observe data by assessing the ability of the model to adapt to real life. We mentioned that. A model that fits well to data is resourceful for quantitative analysis. When we fit our model to data, we can then use it to carry out several analyses, scenario analysis, quantitative analysis, sensitivity analysis, etc. Now, model that performs well post-calibration interval are useful for predictions. And that's one of the major differences between theoretical modeling and data-driven modeling. If you do carry out theoretical modeling, you say the best you can get from it is just to gain insight. You can't use it to make prediction. But if I fit my model to the data and my model matches the data as closely as possible, then I can use that model to do what? I can use it to gain insight into tomorrow, into the future, because already I have trained it to follow the pattern of that data. Do we understand? No response. Do we understand? All right, so some of the methods of parameter estimations, we have the least squares, which we'll be looking at this morning. It minimizes the square difference between model predictions and observed data. Then we also have the maximum likelihood estimation method. Here we are looking for parameters that maximize the data, that maximize the likelihood of having the data. Then we also have the Bayesian inference that combines prior belief and then the data to give us posterior distributions. So those are some of the methods for parameter estimation. Now, the procedure, you have your model, you have your data, and then there is a linking function that we mentioned earlier. Your linking function could be the least square estimate. It could be the maximum likelihood or the Bayesian inference. And then we also have optimization algorithms that will help us optimize the distance between the model and the data. Now, so for this course, we'll be going to looking at examples of models that we want to fit to data. We'll look at linear models and then non-linear models, and we'll also consider deterministic compartmental models that we've been working on. Now, fitting linear models. What does it mean to fit linear models? Now, we have a set of data points. I have a set of data points, x1, y1, x2, y2. And then we are interested in finding a straight line. Now, this is my data set. I have x1, I have y1. Say this is 1, this is 3.2, this is 2. Say I have 2.5, this is 3, 4.6. This is 4, let's say 3 point. So this is my data set. I sent in a data. Have you all downloaded the data set now? I have. So the first one we'll be using is of this form. We have the x column and then the y column. So this is the first point. What's my x1 here? My x1 is what? 1. 1 comma what? 3.2. So this is the first point. This x1, y1. And then this is x2, y2. So I have my data set. Now, I am interested in finding a straight line. a linear model, y equals to ax plus b, that best fits all the data points in my data sets. I want a straight line that closely matches the data points that I have. Now, this is done by finding the optimal parameters. Look at that function, y equals to ax plus b. How many parameters do we have there? What are the parameters there? The parameters. X and y are what? They are variables. A and B are the parameters here. So we are looking for the optimal, the best parameters. So what we are trying to do is we want to adjust these two parameters such that we can find a line that best matches our data points. Let's let's do this. All right, so this is my data points. These are my data points. This is the y-axis, and then this x-axis. So I'm looking for a line, a straight line that best fits these data points. And how do I do that? I'm looking for, now this is the formula or the equation of a straight line, ax plus b. B is the what? B is the what? Equation of a straight line. B is the intercept. A is the what? The slope. Now, so I'm looking for the values of these two guys such that this line closely matches the data points. That is the difference, the distance between each of the points. The distance between each of these points, this point and this line, this point and this line, this point and this line, as closely, they match as much as possible. I can have another line here. Let's assume this is another line here. I can have another line. Now, out of all these lines, which one of them matches the data point as closely as possible? Exactly. That is what we want to do. We are looking for that line that matches this data point. So in doing that, we are trying to reduce the distance between the line and the data points. Is that clear? We want to reduce the distance between each of the line and it. So that process, the process of carrying that out is a minimizing process, which is one of the estimators that we mentioned, the least squares estimate. So in fitting linear models, we have our data points, we have the model, and we want to do that. Now, fitting linear models in R using the LM function. So we want to fit linear models in R using the LM function in R. The LM function is, LM means linear model. So can we go to R now? Have we downloaded the data sets? Where did we save them? Which folder? Okay, you have an R folder created already. All right, so we already know the process of importing data sets from our computer to R. Do we not? You can't remember. We've done it. I think it has been done about 2 times in this workshop. Okay, so let's see, how do we import our data into R? You can open a new R script. You can open Okay. Please, Ikamda members who need your help, please go around and help people who need help. Happiness. Zoom. Yeah, All right. So this is my folder. Then I go to this bar here. Can you see that bar? Or better still, put your cursor on the data for linear equation that we want to use. Put your cursor on it and right click. Are we doing that? Right click, then go to properties. Okay, it's two ops. Fine. Why if you set the Kudaki one? All right, thank you. So, have we clicked on properties? Click on properties. Have you done that? Then you see location. Copy that part. Copy it, the part that starts with C. Have we done that? Copy the parts. Now, I've copied the parts. You now paste it. You have your read.csv. Read.csv. It helps us to read in CSV files into our R. So read.csv. You open a bracket with quotations, and then you paste that thing you copied. Have we done that? Have we pasted it? Have we pasted? Okay, so we are waiting. Don't use this part. This is the part on my system where it is where that file is saved. It's different from your own part. Please, if you need help, raise your hand so you can receive help. It and paste it. Try that bucket. So what we are saying here is that everything here has been stored, saved, and stored into this object named data. Everything on the right-hand side has been stored into this. So I'm naming this data. Have we done that? Have we done that? Copy it. So I have data, the assignment operator, read.csv. That's what I'm typing now. Or should I let's go back to the original. So is it better this way? All right. So just copy it and paste it. We should have done that by now. If you have not done that, please raise your hand. Okay. Now, having done that, copy the name. Go back to your folder and copy the name of that particular file. This one is data for linear equation. I want to copy that name. You can copy the name of this guy. If I try to rename, copy it, and then also paste it here. So look at it. After I copied the first part, there is this part of data for linear equation. This is the name of the particular file we are working with. Data for linear equation .csv. You said what? No space, no space. Slash, put the slash there. So when you copy from your computer and then you paste in R, what you have is a single backslash. You have a single backslash. Now, a single backslash in R is a special character, so it won't work with that. So you have to make it double backslash or a single forward slash. So either you do this, double backslash or a single forward slash, anyone you are convenient with. When you copy and paste, I'm repeating myself, what you have from your Windows is a single what? You copy that part and then you paste it, you will have a single backslash. So you have to make it double, just like is shown here. You double it, yes. You said what? So you are telling that this is a particular file. Where are you pasting it? That's the particular file. This is the path for that folder. The particular file we want to run is this guy, data for, remember there are about 3 files there. There are data for linear equation, data for non-linear equation, and then, so this particular guy is the one we want to work with now. So are we done with this? How many of us we've copied successfully? All right. Now, if you've copied that, you can run it, and then you view the data. Copy it, run it, and view the data. Okay. All right, so when you view, what did it bring out? It brought up a data frame, is it not? It brought up a data frame with how many columns? 2 columns. The X, the independent variable, and then the Y column, the dependent variable. Which 35 minutes? 1 hour. Take your time now. Before it's okay. 35, 50. Oh, yeah, 45. Are we together? Have you been able to view your data as a data forms as a data with two columns? So if you see, just like the data set that I wrote on the board the other time, we have the X values and then the Y values. So in your data frame, what's the first point there? What's my first point? 1, what? The first point is what? 1, what? 6.40340369. So this is X1, Y1. This is my X1, Y1. What about X2, Y2? 2, what? So that's that. Then we want to now visualize. Let us visualize this plot. Let's visualize it. This the particular data that we've brought into our R. So to visualize, we use the plot function. Remember the last time during the simulation, I mentioned that if you have you remember that when we had during model simulation, when we had out that data frame out, how were we able to access the susceptible class, the I class, and the R class individually? We use what? We use the $sign to extract the S class, and then we plot it. We also use it to extract the I column in that. So the same thing for this guy. We have a data frame with 2 columns. You want to extract the X axis or the X column. You also want to extract the Y column. So we use data $X to extract the X column. And then data $Y, it also helps us to extract the Y column. So we want to plot Y against X. Then PCH, what is PCH? PCH is what? Huh? What's PCH equals 16? PCH is the plotting character. And I think we have numbers from 0 to 25, giving you different characters. So for one should be, is it circle? Yeah, I think 1 is this. 16 is that is a solid one. We have 19, we have from 0 to 25 or so, with different characters. So you can try your hands on them. You can change that 16 to maybe 4 and see what it gives you. So for this particular plot, I use PCH equals 16. And that's why it's giving me solid cycles. Then the color is red. We label the x-axis as x, and then we also label y-axis as y. How many persons have gotten the plots? Okay. That's impressive. So if you've gotten the plot, you can try PCH equals, let's say 19 or 12. Who has used a different number aside 16? Anybody? What did he give us? What shape? You used 4. What shape did 4 bring? A triangle is an something like this. Aha. So that means the point will be plotted in this form if you use a different plotting character. So the color is red. So we have now been able to visualize our data. Now look at our data. Is it a linear data? Is it linear? That plot, is it linear? Is it linear? It is not linear. It's not linear. It's not. If it's linear, we'll be having something like a straight line. But we see that it is not linear. Now we want to fit a straight line to it. We are looking for a line that best fits this data. That's what we want to do now. Can we move now? Can we move? Okay, let's wait for 30 seconds. Can we move now? Yes. Okay. So now, let's fit the linear model. We are using this function, the LM function. I said LM means what? LM is the short form for linear model. LM is a short form for linear model. So the LM function, what it's trying to do is trying to minimize the distance between the data point and the line that will fitted, the straight line. It wants to minimize. So it's a kind of, it's an optimization. It uses the least squares error, LSC, to try to minimize. So in the process, it's looking best values of A and B that best minimizes that distance. So we have, let's say, just like I explained earlier, we now have our points. We have our points. So I have my straight line. I'm looking for a line. Okay, let me have another line here. I have 2 lines. This is the first point. This guy, the distance between this point and this line. This is the distance between this point and this line. That distance is called the error or residual. So Now, this other point, there's the distance between this guy. Now I have two lines. Which one do you think? Which of the two lines? This is line 1 and line 2. Which one do you think is closest to each of the data points? Line 1. Now, this is what the LM function is trying to do. It's trying to look for that best line by adjusting the parameters, these two guys, A and B. It will keep adjusting it until it gets the best one that now what? The line that closely matches the data point, such that the distance between the observed data sets and the line, the predicted value, is minimal. It minimizes it. So it gives, so we have something like this, an equation like this. Our SS is going to be, let's say I have AX1 plus what? B minus the first data point there. The first predicted value, Y1. So the distance between these two guys is called the error or the residual. You now square it plus AX2, that it picks the second point, the X point from our data set, plus B minus Y2, it squares it, plus, and then it did it up to the point of the data set. Now it does it for each of using, and then it's adjusting these parameters. Now the one that gives the smallest error, one that it chooses, that's what we call the line of best fit. So that's what this particular function is doing. It works based on the least square error. Now, have we typed that? So here we are saying that the data $s, what is data there? Data $s, we have extracted the X column, and then data $y has also extracted the Y column. So we are looking for, we want to see how this X predicts Y. You know, X is called the predictor variable. Y is the what? Y is called the what? The response variable or the explanatory. X is the independent. Y is the what? Dependent. So it's looking for how do we make X to what? To predict Y. And then we have the tilde sign there. Have we done that? We're able to get the tilde sign on your computer. Huh? All right. So have we run it? Is it running? No effects. Please, can somebody help check? How many of us have run that successfully without error? Okay. So, and then we assign that to model underscore LM. Is that clear? Now, if you attach the $sign, it brings out all the outputs. Attach the $sign to model underscore LM. Model underscore LM. If you attach the $sign to it, what do you have there? What do you have? Okay, have you typed this? The first line. Have you run it? Now go to the next line and type model underscore LM. Only go to the next line, type model underscore LM. Then attach the $sign to it. What did you see? We got the intercepts. What else? What else? What do you see? Residual. What else do we have there? Let me see. Let me try to run it. You see fitted values. You should see coefficients too. What else? The intercepts. Please, somebody needs help there. Sorry, no, not intercept now. The coefficient is the coefficient, you see. You run the, have you run? So where is the, okay, attach the dollar sign to this guy. Yes, attach the dollar sign to it. Now see all this thing it brought.
Okay.
Okay. Can somebody help this woman? So I want to be as fast as possible because we have limited time. So for instance, if I have, can you click on model underscore LM dollar coefficients? Click on the coefficients. What did it bring out? What is the intercept it brought? Model underscore LM dollar coefficient. So it brought what? 0.3 what? 37 74 8. Okay, let me just stop here. That's the intercept, right? And then what else? The data X is what? 3 point what? 135. Now remember where we started from. We are looking for a line, a straight line, y equals to ax plus b that best fits those data points. And we have gotten, so what we did was try to estimate the best parameters, the optimal parameters A and B. So here, what is my A? What is my A here? From the two coefficients it produced, what's my A? Which one is my A? My A is what? 3.13 x plus what? What is my intercept? The B, 0.3074. So this is the straight line that best fits our data sets. This straight line, this line, best fits what? Our data set. And in the process, we were able to what? Estimate these two parameters, A and B, as this guy and this guy. So also run this thing. So let's go to let's now plot. Let's plot. We now want to plot our results. Now, here we want to plot two things on the same. I gave an assignment the other day. When we did model simulation, I asked you to plot what? The S, the I, and the what? On the same plot. How many of us did that? Okay, so it's the same procedure we are using here. So for the first one, which is our data set, we want to plot our data set. plot data, which we did earlier. What does the main give us? It tells us you want to give your plot a title. That's what main does. That main argument. Jesus. Okay. Okay. So the main gives us the what? The title. It's you like a label. You are giving your plot a title. Linear fit, and then PCH is what? Use 16. I like 16. So change, but if you like 19, you can retain it. I like 16. PCH, the plotting character is 16. You know, we used 16 earlier. Is it not? We used 16 earlier for plotting. So you can use 16. The X label, the Y axis, then the Y limb. What does the Y limb do? What's the Y limb? What does it do? The Y limit. What does the Y limb do? The what? Limit on the Y axis. You want to know the minimum and the maximum. You know, at times you make your plots, and then the plot is not, let's assume I have a plot like this, for instance. This is my plot, and then this is my axis. This is where the axis is. And then the value, the plot, sometimes it overshoots the plot area, and then you cannot see these parts. You are only seeing just these parts. So what you do is what? You increase the limit of the y-axis using y-lim. Do we understand? Sometimes you plot and it's not showing you everything, all the part of your plot. Some parts are cut off. So you use the y-lim to set the limits, the minimum and then the maximum. So now for our data sets, we use plots. Now, because we want to put both the fitted values and our data set on the same plot area, we'll now use what? Lines. You won't use plots now for that. You use lines. If you did that assignment correctly, you use plot for the data set. Now for the model, the fitted values, we use lines. So this is what we are trying to do. Now for lines, what did you observe? What do you observe in the second line of code compared to the first one? Look at all the ingredients of the first one. What ingredient does it have? It has XLab. It has what? It also has what? Y label, Y lim, and all that. But for lines, we don't have it. Why? Who answered that question for us? Why are we not having it? Why are we not having XLab? Why are we not specifying it? Is that? Can you come again? We have it already. Thank you. So there is no need of repeating, because our motive is we want to put those two quantities on the same plotting area. We want to plot them together. So we don't need to specify the XLab and the Y label again for the lines. So for the lines, we have model $fitted values. So what this does is that in your model, once you attach, like I mentioned, it extracts the fitted values. It extracts the fitted values. So the color is blue. How many of us are on the third line of code now? Legend. Are we on legend now? Okay, let's wait. Let's wait. Why are we using legend? Why? Why the need for legend? Huh? To what? Because we have more than one line. You need to know which one is which. We have more than one line. Which is which? Are we together? So legend, the first argument there is you want to put the location where you want your legend to be situated. Where do you want your legend to be on the plot? Sometimes you will need to, you first plot it, then it now gives you an idea of where the legend should be. So look, this is my plot area. This is my legend can be here. I can decide to put it here. I can decide to put it here, here, or here. So if it is here, if I want it here, what will I label it? This is what? What position is this? Top left. This is top left. That means if I specify top left, the legend will be here. We specified bottom right. That means our legend will be here. That's what that means. Bottom right, you can specify center depending on, let me go back a little. Look at my plot. Look at this plot, everybody. Sorry, I went a little back. So where do you think I can place my legend? There are spaces on the other side, and then there are spaces below here too. So where is best to keep my legend? Either I keep it over there, or I put it what? If you put it at the center, what happens? It will obstruct the line there. So your data, when you plot it, it gives you an idea of where you place your legend. All right, so we can continue. So, and then we also have the legend, the name we want to put. We have our model. We are familiar with this, the C command or the C function. What does it do? It does what? It combines. We are combining both model and data. And then color also. So this means that what? Blue corresponds to what? That means my model will be in which color? Huh? Look at the first combined function we had there. We had C model, comma data. So the first one is model, which corresponds with color blue. Can we see that? That means then my data corresponds to what? Color black. Color black. Are we together? Then the PCH. We also combine that too, because we are looking at two. So you can use 16, change this to 16, change this guy to 16, change the 19s to 16. But if you like, some persons like 4. So you can use 4 too if you don't like, if you don't like 16 or 4. So PCH equals, we are combining Na and 16. What does that mean? Na means what? That means you want it, you say don't put anything there. You want it to be missing, not available. Look at it. Which one corresponds to Na here? Which of the two quantities we are looking at correspond to Na here? Model, is it not? The first one. The first one corresponds to model. Na is the first one there, which corresponds to what? Model. Why are we saying model should be Na? Why? What's the reason? Why the legend we labeled model? Why should it be Na for PCH? Why? What is the reason? Who knows? Who is helping us? Nobody is helping us. So for our model, look at it, we use line. For the data set, what did we use? We use points. For the data set, we use points. And then the point in this case is we specified as 16 or 19. That is why, look at it, for data, the second element here corresponds to this 19 or 16. Why the model, which is line, is what? So you're saying for this first one, don't put anything. Let it be Na. For model, don't put anything. Because the model is line, not point. Yes, ma'am. The one after it, this guy, it's 1, comma Na. So that second one is line type. Line type. Look at it now. In this case now, which one corresponds to my 1? Which one corresponds to 1? In our legend now. Is it model or data? Model corresponds to 1. So we are looking at, because our model, we plotted our model with line. The first one, data set, was with points. So that is why when we got to the place for points, the model is not available. You are telling it in there. But when it comes to for data, put 19 or 16. Now, when we got to line type that specify the type of line we want to use. For model, we said use line type 1. You can because we are using points. You are saying what? Leave it empty. Don't use anything. Do we understand? Are we following? Yes. LTY, yes, LTY. Line type, LTY. Then the CEX, what is the character expansion helping us to do? What is that one helping us to do? Who can tell us? It helps us to what? It helps us to either we want to adjust the size of the legend. If I have L type Y, maybe so your legend can be in this way, depending on how you want it to be, the size you want. So you use that, use the CEX to adjust the area of the legend. So are we done with that? Can we move? How many of us have plotted it? Only a few hands. Let's wait for others. Okay. Have we done that? Any questions so far? Yes. What's the question? Help. Okay. Somebody needs help over there. Can we move now? Have we plotted? Who has not been able to plot? So if you have plotted, you can try your hands on some of those the legend function there, the legend command there. You can change maybe CX, you can increase it or decrease it and see it, and then the colors too, or the position. You can decide to use top right or top left or bottom right, and then see what it brings out. We are waiting. Are we there? Are we plotted now? Can I move now? Okay. So this is our linear fit. Remember the aim, the main, we title the main linear fit, and then we have our legend. The legend, the line is for the model, y the dot, data. So this is the line of best fits. The line that best fits this what? The data sets. That means this line has, look at it, the distance between this guy, this first point, and this, all the data points, and then the line. We've tried to minimize them as much as possible. We want one that is closely matches that data sets. And in that process, we estimated the parameters. We estimated parameters A and B. Were you able to extract? Did anybody extract the fitted values? Did we extract the fitted values to see them? Huh? Extract the fitted values, model dollar fitted values, and see. Were you able to extract it? So those are the fitted that we actually, that line. Those fitted values were what we plotted as what? As lines. Then you can also plot the residuals. The residual is the difference between the observed data and the what? The predicted values. Are we together? All right, so we've seen how to fit linear models to data, and in the process, we were able to estimate the two parameters. Now let's look at nonlinear models. Nonlinear models. Nonlinear models. fitting nonlinear models using the NLS function. This is nonlinear least square. So what's the first thing we need to do? Bring what data into R. So let's do that. Import your data into R. That's the second data set. Let me see. Import your data set, and then you store it to this object named data underscore NLS. We have our read.csv, and just like the previous step, go to your folder, copy the path, and then paste it. And also copy the name of the file. This file now is data for nonlinear equation. The first one we did was data for linear equation. So copy the file, the name of the path and the name, and then you do that. I hope we're on it. Remember to change, you either make your backslash double or you use a single forward slash. For the path, either you use a single forward slash or the backslash, you double the backslash. Have we imported? That should not take us a lot of time because we've done it earlier. We did it earlier for the first model that we fitted. So for this one, it shouldn't take any time. You go to your folder, you can either go to the parts, the menu bar, and copy it, or you right click on the particular file, and from properties, you are able to get what you need from the properties of that file. Are we together? You need help, sir. NLS. Please, can somebody help him? Did you put the part correctly? Did you read it incorrectly? Once you import it, you can load the data. And then what are we doing on the next line? What are we trying to do here? We are what? So firstly, remember we use the data. We want to maybe we should view the data underscore NLS first. View it to see it. Now, having viewed, if you view it, then we'll see that it has how many columns does it have? How many columns? 2 columns labeled X and Y. So we can extract each of the columns, just like we've been doing, just as we did for while we're doing model simulation. So you can extract the X column. So we extracted the M, and then we store it as what? This object Y. We did the same thing for the S column. Have we done that? Are we there now? Can we forward? Who said no? Let's see. Let's wait for. Do you need help or you need time? Ah, she needs both time and help. Who is going to give her? Somebody should help our mommy over there. We are waiting. So we are fitting exponential models. And the expression is non-linear. Remember the linear model we did when we were fitting linear models. We didn't specify the particular model. Why? But this guy now, we are specifying. How do we represent linear equations or linear functions? Mathematically, how do we represent them? Y equals to what? Mx plus c, ax plus b, the same thing. Linear models, any linear model, the same function. But non-linear models, we have how many? How many non-linear models do we have? 3K. How many non-linear equations do we have? Infinitely many. We have infinitely many of them. Trig, exponential, name it. Cubic, quintic, quartic, several of them. So you need to specify the particular one you want to model, unlike for linear model where it is the same, ax plus b, y equals ax plus b. So we didn't, we just use only the predictor value and then the predictor, the independent variable and the dependent variable. So for this, we had to specify this guy, the exponential function here. Then start equals to what? So what we are doing here is we are giving the initial guess. We want it to fit this model to the data we have supplied. Did we plot that data? The data, did we plot it? Okay, exercise, let's plot the data. Let's plot the data to view it. So let's plot the data. We should be able to plot this data now. By now, everybody plots the data without looking at my code and without copying from anywhere. We should be able to plot ourselves. So let's plot this data before we continue, so that we can visualize it. Use the plot function, plots. Plots. Who has plotted? One person has plotted, 2 persons, 3 persons. Okay. Which plot is this one? Okay. Have you plotted it, ma? Yes, ma. Yes, and do the necessary adjustments. What are we plotting? We are plotting the y against the x. So here now, we've assigned data underscore NLS to y. So you have your y, your x, you have x here, you have y here, and then here. Yes, x. So this now is now non-linear. This is for the first one. So you have non-linear fit and all that. Yes. So you make the adjustments. This is not well done. No. Which one is this one? We look at the Y limb. You have used Y limb as 350. That's what you must have done. See your Y limb, 341. So the Y limb there is just 34. It's not, yes, ma'am. Ah, so have you been able to, okay, we need more people to plot that. So have we plotted? All right, so I was saying that we choose some initial guess. For our A, we chose 3, and then B, we chose 0.1 as initial guess. So once you've done our fitting, you can find the summary of the model using summary model underscore NLS, and we plot the results. Remember, we've extracted the X column and the Y column, and we've assigned them to the variables X and Y respectively. So that's why we have here on the X axis, we can put X because we've done that assignment earlier. And we can have Y, and then the title is nonlinear exponential fit. So that's for the data set. Then for the fitted model, we use lines. We want to plot the two of them on the same, we want to have them on the same plot. So we use lines. The X axis, and then the predicted values. We use color for red, and then the line width is 2 to help specify the thickness of the line, the thickness of the line for your model. You need help or time. What after 1? The bracket. Huh? Okay. Were you able to do the summary of model underscore NLS? No. Well, let me see. Open this. Run this. Let me see what it brings. This summary. Remove the. Run it. Unable to find. Why? Did you run? Run from the beginning. Let us see. Wait. Okay. Mhm. Mhm. Right. Okay. This copy summary model underscore NLS. And no, no, no. And then you can remove it. NLS A B and data for and B. Mm. What is wrong? Why is it not? Is there an issue with it? Let me see. Okay. Have you been able to plot? Okay. Are we done plotting? How many minutes more should be given for us to plot? 5 minutes. Have you plotted, sir? Oh, yeah. Huh? Your laptop. Okay. Who has plotted? You have been able to plot. Okay. Have you plotted over there? Yes, you. Yes, you. Keep talking schematic diagram there. Have we been able to plot that? So if you do that, we should get this fit. You should get this fit. And then in the process, we should be able to, we have estimated the parameters. What are the parameters there? What are the parameters in that model? What are the parameters in this model? A and B. So you have estimated the parameters. If you do your summary model underscore NLS, you should get the summary of everything there, including the parameters that were estimated. So we want to move to the last one, the last model, another nonlinear model. Another nonlinear model. So that one, you'll be doing that yourself. We want to fit the logistic growth model. The logistic growth model. So if you are done with this, go to your folder in R and then read in this data. Read in this guy, the logistic growth model. So we have Y, it's also a nonlinear model. 1 plus exponential minus R x minus x naught. So we want to fit this model to that data, the third data set that was sent to the group. Let's go and bring it into R. That's data for logistic growth model. What is it now? What to call it? New demo. So, what is the update now? Hello. All right. So have we done that? Have we brought in our data into R for logistic growth model? So bring it and then store it to an object that you name data logistic. The same process we did for the first example and then the second example. I think we should do this ourselves. Should we try this model? It follows the same format with the one we did just now. The exponential, the only thing we are changing is this model. How do we type in this equation in R? How do you type it? Huh? Do we know how to type this? Just follow it now. K, capital letter K over 1 plus, we should be able to type this in R. Maybe that should be the first exercise that we should do. How do I type this guy into in R? So are we reading the data? It seems the default answer is no. By default. So I'll give this as an assignment. Let's do it. Follow the same procedure. Model this. Then you have your NLS. Use this function. And then you put in the model here. You type in that model. Then you put your initial guess for each of the parameters. How many parameters do we have here? How many parameters do we have for this? Huh? D2 is not 2. We have what? We have, which one do we have there? We have K, which again? We have R, and which one again? We have X naught. So we have 3 parameters. So we'll have start equals list, K equals, you can use K equals 100. What's the question? We are looking at the third model already. This guy. We are looking at this model. This is the third example. A logistic growth model. So, and we said it has 3 parameters. It has the K, it has R, and then it has X naught. So we need to find some initial guess, just like we did for the second example, where A equals to 3 and B equals, so the optimization algorithm will work with those initial guess, and then it begins to find which particular parameter, it begins to do some adjustments, which parameter will give us the line of best fit. So our initial guess, so we have K equals 100, R equals 1, and X naught equals 5. So let's use this. K equals 100, R equals 1, and X naught equals to 5. So let's use this as our initial guess and fit that model to the data that we are given. Sorry, okay, X naught, yeah. Question? Is somebody saying something? Are we trying it? Who is trying this? Please, let's try it. Let's try it. Let's put our hands to work. Let's try it. So what do you do next? After this, what are we going to do? I want to what? Extract. How many columns does it have? The data underscore logistic. When you view it using a view function. How many columns? 2. So you can extract each of the columns and then store them as, give it a name, maybe X, just like we did for exponential. You extract, yes. You said what? How can you do? Okay, the X naught. Okay, she's saying how can she put X naught? You can just put X0. Just in your R, just type X0 to signify X naught. Thank you very much. So just X0. So X0. Well, you need to be able to code this correctly. That's the first thing we should do. If you can't do this correctly in R, then there are issues. So how do we do this? We have K over what? 1 plus what? We use X. Is it not? Remember how we did for exponential, exponential what? Exponential bx. Exponential b then times x. So the same thing we do for this. Exponential, and then you put in bracket correctly. Hey, sorry. Okay. You are comparing. Have you reading the data? All right. Did you run it? Run the two guys. Okay. So what's the next thing? Just follow the other one. Follow the process. So, okay, maybe we shouldn't plot now. You can do this. The model, give it a name, and then NLSY. Replace this guy with the new model. Okay, maybe I should just display it, but we don't have time. I want to end this section now. So probably in the next class, we'll look at it. But meanwhile, the next class, the virtual, we still have virtual class next week. No, it's an assignment. So we'll do it, and then when we meet virtually, we'll do the correction to the assignment. But it's very simple. Just follow the procedure for the first one. They follow exactly the same format. Just follow it. Put your initial guess. I've given you the values to use. K equals to 100, R equals to 1, and X naught equals to 5. So if you do that correctly, you should have something like this. If you do it correctly, you have a fit that goes like this. So at this juncture, we want to call it a day. Thank you, everybody. Thank you, SARS and MAS.
All right, so let's appreciate our facilitator once more. All right. So that was a nice session and a beautiful one. Thank you very much for that session, sir. Okay. Okay, question. Okay, let's take help or question. Help. Okay. All right, sir. I can see that everybody's really engaged. We're trying out many stuff with our hands. So that's beautiful. Hope the quotes are running. It's not running, but it's scrolling. or is working? It's not working. So if you need help, please let's signify so that people can come around and assist us. Okay. Okay, somebody over there.